Hi friends, today we discuss about the Norton's theorem. Norton's theorem, also known as the Mayer-Norton's theorem, was independently developed in 1926 by Hans Ferdinand Mayer and Edward Laurie Norton. Norton's theorem, a fundamental concept in electrical engineering. It simplifies complex linear circuits into a single current source in parallel with a single resistor, providing an equivalent circuit for analysis. First of all, we know about the statement of Norton's theorem. Any linear network can be replaced by an equivalent network having a single constant current source called Norton's current IN or I subscript N and a single parallel resistance called Norton's resistance Rn or R subscript N. In simple terms, Norton's theorem states that it is possible to simplify any linear circuit, no matter how complex, to an equivalent circuit with just a single current source and parallel resistance connected to a load. Norton's theorem allows you to replace a complex linear circuit with a simplified equivalent. The equivalent circuit means it consists of a single current source in a parallel with single resistor, where Norton current IN or I subscript N means the current in the equivalent current source is the short circuit current of the original circuit. Norton resistance Rn or R subscript N means the resistance in the equivalent circuit is found by looking back into the terminals of the original circuit after removing all voltage and current sources. Next, we discuss about the explanation of the Norton's theorem. Consider the network as shown in the circuit diagram. The first image shown the electrical circuit diagram provided depicts a combination of a series and parallel resistors connected to a voltage source E, where E represents the voltage source or electromotive force, means EMF. R1 means a resistor connected in series with the voltage source. R2 means a resistor connected in parallel with the combination of R3 and RL. R3 means a resistor connected in series with RL. RL means represents the load resistor, and A and B represents terminal points in the circuit. To analyze this circuit, it's important to understand how resistors behave in series and parallel configurations. So we know that series and parallel configuration definitions. First of all, series configurations means resistor connected in series have the same current flowing through them and their total resistance is the sum of individual resistances. The formula for calculating the total resistance equals to R1 plus R2 plus R3 plus R4 and so on Rn, where R1, R2, R3, R4 represents the resistances of individual components. Next, parallel configurations mean resistors connected in parallel have the same voltage across them and their total resistance is calculated using the formula 1 by R equals to 1 by R1 plus 1 by R2 plus 1 by R3 and so on 1 by Rn, where R1, R2, R3 and Rn are the individual resistance. The second image depicts a circuit with a voltage source A and three resistors R1 and R2 and R3 connected in a combination of series and parallel. Resistors R1 and R3 are in series with each other and their combined resistance is in parallel with R2. Next, we find out the value of Norton's current means IN. That load resistance is disconnected from the terminal A and B. Load resistance refers to the opposition that a load offers to the flow of electric current in a circuit. The two terminals are short as shown in figure. When Norton's theorem is applied with two terminals are shorted, the circuit is simplified into an equivalent current source in parallel with a resistance. The short circuit current is the Norton's current IN. The effective resistance as seen by the terminals A and B is effective resistance equals to R1 plus R2 by R2 R3 by R2 plus R3. Effective resistance, also known as equivalent resistance, is the total resistance of a circuit that an external current source would encounter when applying a single voltage or current to the circuit. If represents the total opposition to current flow in a circuit where multiple resistors are connected. Effective resistance equals to R1 plus R2 R3 by R2 plus R3. The above equation we take LCM. Here, the denominator of a function is R2 plus R3 and 1 means 1 into R2 plus R3, that is R2 plus R3. Here, the denominator R2 plus R3 into numerator R1, it means R1 into R2 plus R3. And the next step, the denominator R2 plus R3 and R2 plus R3 are cancelled. So, remaining term, the numerator R2 R3. The final output will comes effective resistance equals to R1 into R2 plus R3 plus R2 R3 whole by R2 plus R3. Above equation, we applying multiplication of all terms. Effective resistance equals to R1 into R2 equals to R1 R2 plus R1 into R3 equals to R1 R3 plus R2 R3 whole by R2 plus R3. Finally, effective resistance equals to R1 R2 plus R1 R3 plus R2 R3 whole by R2 plus R3. This is the equation number 1. The formula for the current driven by the source is I equals to E by effective resistance. This is the equation number 2, where I is the current, E is the voltage, and effective resistance. We know the amount of current available from such a source is given by the ratio of the voltage across the voltage source to the resistance of the resistor. Already we know the Ohm's law, E equals to IR. It is a fundamental principle in electronics stating that the voltage E across a circuit element that equals to the current I flowing through it multiplied by the resistance R of that element. So, the formula of current I equals to E by R, where E represents voltage measured in volts. I represents current measured in amperes. R represents resistance measured in ohms. This relationship allows engineers and students to calculate any of three variables E, I, or R if the other two are known. From 1 and 2, effective resistance value substitute in the equation number 2. So, I equals to E by R1 R2 plus R1 R3 plus R2 R3 whole by R2 plus R3. Here, the denominator R2 plus R3 that is converted to the numerator. So, E into R2 plus R3. Finally, we get I equals to E into R2 plus R3 whole by R1 R2 plus R1 R3 plus R2 R3. This is the equation number 3. The short circuit current is the Norton's current. Norton's current is defined as the short circuit current across the terminals of a circuit. This current is a key parameter in Norton's theorem, which allows a complex network to be replaced with an equivalent current source in parallel with a resistor. IN equals to current through R3, means Norton's current formula IN equals to I into R2 by R2 plus R3. This is the equation number 4. From 3 and 4, the formula of current I is substituted in the equation number 4. we get In equals to E into R2 plus R3 by R1 R2 plus R1 R3 plus R2 R3 into R2 by R2 plus R3, where the numerator E into R2 plus R3 and denominator R2 plus R3 are cancelled, remaining numerator term E. Finally, Norton's current IN equals to ER2 by R1 R2 plus R1 R3 plus R2 R3. This is the equation number 5. Next, we find the Norton's resistance Rn, means R underscore N. The load resistance RL is removed across AB and the circuit is open at these terminals. The internal resistance of the battery is assumed to be 0. It means when a battery voltage source is removed, it is replaced with a short circuit. This is because an ideal voltage source has zero internal resistance and a short circuit represents zero resistance. The Norton's equivalent circuit then consists of a current source in parallel with a resistance, where the current source value is the short circuit current of the original network. The Norton resistance is given by the effective resistance at the terminals AB. Simply, the Norton resistance, also known as the output resistance or internal resistance, is indeed the effective resistance seen at the terminals AB when Norton's theorem is applied to a circuit. It represents the resistance that the circuit appears to have when viewed from the terminals after all voltage and current sources within the circuit have been replaced by their respective short and open circuit equivalents. It is given by Norton's resistance equals to R3 plus R1 R2 by R1 plus R2. This is the equation number 6. Simply, this equation represents the total equivalent resistance or Norton's resistance Rn of a circuit. The Norton's equivalent circuits are shown in figures. The first image depicts a Norton's equivalent circuit. The load resistance is removed across AB. This involves temporarily setting all independent voltage sources to 0, short circuit them, and all independent current sources to 0, open circuit them. The resulting resistance between the two terminals is the called Norton's resistance. The second image depicts a Norton's equivalent circuit which is a simplified representation of a more complex circuit. It consists of current source IN provides a constant current. Norton's resistance Rn connected in parallel with the current source representing the internal resistance of the original circuit. Load resistance RL represents the external component or circuit connected to the terminals A and B. This equivalent circuit is useful for analyzing the behavior of a circuit with respect to a specific load. The current through and voltage across the load resistor can be determined using circuit analysis techniques. This is the concept of Norton's theorem. Thank you very much. Padmam Hemam.